We've been using partial differentiation to find partial derivatives of multivariable functions, and we've been using all the rules that we learned back in Calculus 1 for differentiation, including the chain rule. But what I want to do now is I want to take a little deeper look at the chain rule and see how we would apply it for a couple of different cases. Now, recall the chain rule. We have something like this. We have y equals, I don't know, h of u, where u is equal to some function of x. In other words, we have and writing this out, we would have y is equal to h of g of x. And what we learned with the chain rule was that if we want to find the derivative of y with respect to x, we kind of work our way from the outside function in. So this would be the derivative of h with respect to u, and then times the derivative of u with respect to x. In other words, using Leibniz notation, we would have dy du du dy. I mean dx. Sorry about that. And this was how we wrote the chain rule. Now, we're going to see how might we apply that in a couple of different cases with multivariable functions. The first case is when we have, well, let me show you. Let's suppose we have w equals x squared plus y squared. And let's suppose that x and y are functions of t. So in other words, x is equal to cosine, let's say 2t, or cosine squared t. And let's suppose that y is equal to sine t. And let's suppose that what we want to find is dw dt. Okay? So we want to apply the chain rule. So here we go. Now, there's a couple of options. First of all, you notice this is not a partial derivative here. We could, if we wanted to, just put the cosine squared t in place of x and the sine t in place of y and just differentiate just like we did back in Cal 1. But let's take a look at this and see an alternative to that. First of all, what I want to do is I want to take the derivative. What I'm going to do is I'm going to take the derivative, the partial of w with respect to x. And then I want to multiply by the derivative of x with respect to t. See, it's like I'm going from the outside in, taking the partial with respect to w, or the partial of w with respect to x, times the derivative of x with respect to t. Then I want to do the same thing over here. I'm going to take the partial w with respect to y times the partial of y with respect to t. So we're working our way on the outside in, right? So look, let's see how this would work out. We've got the partial w with respect to t. Okay, so this would be 2x. Now the derivative of x with respect to t, well, that is 2 cosine t sine t, negative sine t. Okay, that's that. Okay, that takes care of that part. Then the next part, partial of w with respect to y, that'd be 2y. And then dy dt, that would be a cosine t. And there you have it. Now, we're not exactly finished because I need to I want everything in terms of t. So I've got this 2 and this 2, that's negative 4. In place of x, I'm going to put cosine squared. And then I've got cosine t, sine t. And then over here, in place of y, I'm going to put sine t. Now, and of course, we can clean that up a bit if we want to and call this negative 4 cosine cubed t sine t plus 2 sine t cosine t. And we could play around with the identity, trig identities and clean this up a bit, but that is how we find dw dt. Now let's look at an alternative method. And what I want to do is I want to substitute in. So I'm going to do this. I've got w is equal, in place of x squared, I'm going to put cosine squared t. And in place of y, I'm going to put sine t. Okay. So notice this is x squared plus y squared. Now let's see what this gives us here. We've got cosine to the fourth t plus sine squared t. Like that. Now let me differentiate. Now this is just a single variable here, t. So I've got dw dt is equal to 4 cosine cubed t, and then derivative of cosine, which is negative sine. Put a negative in front. And notice that's this. Okay. Plus, now let's take the derivative of this part over here. This is going to be 2 sine t cosine t. See? The derivative of the outside times the derivative of the inside. Now, this is when x and y are functions of a single other variable, t in this case. They're just functions of t. Now, let's suppose this is one case. Now, let's suppose that x and y are not functions of just a single variable, but let's suppose that x and y are functions of two other variables, like s and t instead of just t. So let's take a look at that. Let's suppose that we have this function, x squared plus y squared. And let's suppose further that x is equal to t cosine s, and y is equal to, let's say s sine, well, let's not do that. Let's say it's equal to t squared sine s. Let's do that one. Okay, now w is a function of x and y are functions of a two variable situation. Okay, so x and y are multivariable functions. Before, in the previous example, x and y were just single variable. There was one independent variable. Now x is a function of two independent variables. Y is a function of two independent variables. So let's talk about how we would approach this. Let's talk about the partial of w with respect to t. Okay? And also, we're going to talk about the partial of w with respect to s. So we're going to talk about those two separate situations. Now let's see what this would be. Partial w with respect to t. Okay, we're going to take partial w with respect to x times partial x with respect to t. In other words, I'm getting the derivative with respect to t taken care of with the x function. Then I want to add that to partial w with respect to y. Okay, so now I'm on to the y's, times partial y with respect to t. Okay, so there's that one. Now, if we look at it the other way, we're going to go to each variable, x and y, and we work our way inside. So this is going to be partial w with respect to x, partial w with respect to s, plus partial w with respect to y, partial y with respect to s. And there it is. Those, so this is the way we approach it when we have two independent variables. Now, once again, we could, from the very beginning, just substitute t cosine s in place of x and t squared sine s in place of y, and then just differentiate, in a straightforward fashion, doing partial with respect to s and partial with respect to t. But we don't have to do that. We can just go through here and let's see what this turns out. Okay, we'll do this first one, this one right here. Okay, partial w with respect to x. So that's going to be 2x. Partial x with respect to t. That's cosine s. Okay, then plus, okay, we got partial w with respect to y. That's 2y. And then partial, uh, partial y with respect to t, that's going to be 2t sine s. So there you have it. Now, I want to clean this up just a bit. Let's see here what we've got. We've got 2x, and I'm going to leave a little blank here in place of x, cosine s, plus 4, I'll leave a blank for the y, t sine s. And what I want to do is I want to put in place of this little first blank, the x, what x is, and that's t cosine s. And in place of the y, I'll put t squared sine s. There we go. Now, this whole thing, let me go ahead and clean it up. This is 2t cosine squared s plus 4t cubed sine squared s. Yeah, so this is the derivative. This is partial w with respect to t. Now we could go through that same procedure for partial w with respect to s, but I want to move on and let's think about something else here. Let's suppose that I let's suppose I've got this situation here. I've got x squared y cubed plus 2x plus 3y equals 4, something like that. And I'm going to rewrite this way. I'm going to rewrite this as f of x, y is equal to x squared y cubed plus 2x plus 3y minus 4 equals 0. So let me do that. I'll just say this is w here. Now, note this, that we have f of xy equals 0. Now, so let's just think about this, and let's suppose further that w is equal to this. Let's suppose that y is equal to some f of x, some function of x. Okay. In other words, this is like in calculus 1 where we had an implicit differentiation situation where we had x's and y's together, and we understood that y was the dependent variable. It was dependent upon x. So we have here that y is a function of x. Now, what I want to do, I want to go through here and let's try to find dw dx. Well, we're going to use the chain rule. We're going to take the partial with respect to x times dx dx, right? Okay, which is just 1. So what I'm doing is I'm kind of making it fit in to what we just looked at with the chain rule earlier. Plus the partial with respect to y. Now, dy dx. Now, of course, remember w is equal to 0, so the derivative is just going to be 0. So this is equal to 0. dw dx would be 0 because it's equal to 0, so the derivative would be 0. Now, let's see what we have here. First of all, this dx, the derivative of x with respect to x is 1. So let's do this. Let's take the partial with respect to y and times dy dx, and let's move everything else to the other side. So we have negative fx, xy, and I'll just leave off the dx dx. Okay, so we have that. Now I want to do this. I want to say dy dx is equal to negative partial with respect to x over partial with respect to y. Okay, so if you notice, what we've just found is dy dx, and we did it with partials. Now I want to look at this thing right here. I want to see if I can show you how it works. So here's what we started with. And what I want to do, I want to rewrite this way. X squared y cubed plus 2x plus 3y minus 4. Okay, of course, equals 0. Now, let me take, I, I want to go through here and differentiate the way we've always done it back in Calculus 1, implicit differentiation. So I want to go through here and differentiate this first product here. So I've got 2x y cubed plus 3x squared y squared. See, I just used the product rule on this. Derivative of the first times the second plus the derivative of the second times the first. Now, I've got derivative of this 2x is 2, plus here is 3y prime, and that's it. And actually, I forgot something here, right? I need to tack on a y prime. You don't want to forget that, okay? Because I'm using the chain rule, right? Derivative of the outside times the derivative of the inside. So I said 3y squared times the derivative of y with respect to x. And of course, this is equal to 0. Now, let me gather my y primes together. And I've got 3x squared y squared plus 3 y prime. And let me move everything else to the other side over there. Or let me not move it to the other side yet. Let me just write it here. So it looks like I've got 2xy cubed plus 2 equals 0. Now, let's think about this right here. 2xy cubed plus 2. If I were going, notice if I said this, if I said the partial with respect to x of this original up here, notice that would go like this. I would take this first term, and this would be 2xy cubed plus 2. That's the partial with respect to x. Well, that's what this is right here. Partial with respect to x. Then if I said, well, let's take the partial with respect to y. Well, that is going to be 6xy squared. Actually, I was looking at the wrong thing. Sorry about that. Let me erase this. Okay. I was looking at this instead of this. So this would be 3x squared y squared plus 3. Okay. Now, if you look, that's this right here. This is partial with respect to y. So this is kind of what we had before. We had partial with respect to y, dy dx, see? partial with respect to x. Now I move that over, and you'll see that dy dx is equal to 2xy cubed plus 2 with a minus out front, right? I moved it over to the other side. And down here we have 3x squared y squared plus 3. But the point is, this implicit differentiation, this is like a shortcut to the implicit differentiation. If you want dy dx, take the partial with respect to x, the negative of that goes in the numerator, divide it by the partial with respect to y. And that's a shortcut for implicit differentiation. Now we can also do the same thing if we have more than just x and y. In a similar way, we could show this. We could say, well, let's suppose we want to find the partial of z with respect to x. Well, that's going to be, the numerator is going to be partial x, xyz, over partial z, xyz. And you could do the others, but you can see partial z with respect to x. We could do partial z with respect to y, and we could do partial z with respect to y, and that would be negative partial y, xyz, over partial z, xyz. Yeah. And we would say that, of course, this goes without saying that partial z can't be equal to 0. We can't divide by 0. But these are some ways that we can, some shortcuts. This is something that we can use partial differentiation to make things a little bit easier. Like, for example, back when we were talking about implicit differentiation, if I was going to use implicit differentiation here, you notice I would have to use the product rule for this one. If I do partial derivatives, there's none of that. I don't have to do it. So using partial derivatives made things a little bit simpler.